Good evening to you all. I'll be just talking about the spatial clustering. So this is one of the important aspects in spatial analysis. So I'll just briefly have a set of objective which I want to achieve in this lecture. The first one is basically to get to know what exactly is the meaning of spatial process and what is the impact of those spatial processes. Then how do we why do we need clustering? So what is the purpose of having any specific clustering techniques? What exactly is the clustering? So basically we'll try to understand the definitions, what exactly is the clustering, and then we'll also try to understand how to measure the different clustering outcomes. So like you are having one particular algorithm, so now we would like to know that how better that tools is able to give some measurement, that is the process is clustered or not clustered, this kind such kind of things. The extension of these can be done also in term of simulation of occurrence. So simulation of occurrence generally means that you may be having a one snapshot of data sets, and that may look like a clustered one, but you would like to know how likely that particular data set is to which is representing a cluster in compared to normally or non-cluster data sets. So I'm not covering about the last one because due to the paucity of the time. So let's understand what exactly is the clustering processes. So before going into that questions, let's have this example of these two data sets. One is basically you're having a point data source. This is basically a SNOWS map. It's basically a cholera based data which has been collected by Snow Jordan, and what he has done is he has just mapped each of the individual who had died due to cholera and then try to find out its locations. And he also mapped basically 5 tube bells around the people who have died, and based on that he could make assumptions and finally discovery that cholera is basically a waterborne disease. So in this case, basically what happens is each individuals are being marked as the locations is being marked as a point. So over here, each point is actually a kind of event on which the measurement has been carried out. On the right side, the aerial group, basically what we do is we'll having if some kind of boundaries or aerial boundaries, or in GIS terms we call it a simple polygons, and within that polygons we may be having some aggregated values. So like on the left side we are having an individual values for each of those incident, and on the right side within a polygons we'll be having an accumulated values. So like within this polygons we can count how many incident has occurred, and that will be measured and marked into one of the polygons. So on the right side basically just represents the snapshot of different COVID cases at the beginning of March. So that's what is being shown in these cases. So these two are basically two different kind of data sets. One is aggregated one, another one is the individual. So aerial is basically aggregated values, where the point data sets are actually an individual incident values. So let's understand what exactly is the spatial processes. So generally in any kind of geographical area, what we expect is that if any event or any kind of activity which is going to occur at one place, so that places may the occurrence of those places may be random. So it means like there's no spatial dependencies. So one event which has occurred over here is equally likely to occur here, and so on. So it means like we'll be having a kind of distributions which gives the a kind of processes where each of those incident or occurrence are equally likely within the area. So this is the which we call is the random processes, where in some cases we may be having a quite regular deterministic processes where like in this cases any values more than zero point 0.5 on x-axis, where there is a chance of occurrence of an event, or on the less than the value on a particular range, that is the zero point 0.5 values, there is no chance of occurrence any event. So in this case, if I would like to model a specific incident of an activity, then what or incident of any activities, so in that case one simple solution says that any values more than x 0.5 is any event which is having a locations more than 0.5 will there will be an event occurrence, another one the event will not occur. So that's basically completely deterministic models. There's a no variations of on a spatial or stochastic variances not there. Then we are having a kind of stochastic processes, which is a kind of processes which is somewhat regular. So it means like we know a slight positions based some event, but within the event also within the specific locations, the occurrence of that event is not fully bounded. So it means like the values, even though the any values on this cases or x location which is more than 0.5, the event is going to occur, but the occurrence of that event is equal likely. So it may occur, it may not occur. So it's like high. So any values more than x in this case is the event is most likely to occur, but that doesn't mean that it is definitely going to occur. So generally in real life or in any kind of spatial processes, we get a mix of these. So it means like there will be a few variables which will be linked to a spatial location, and as well as there will be some statistical process along with that. So combinations of those two things is going to generate or create an event. So generally these processes which are spatial dependent or spatial independent, so these are the space independent, and this is completely spatial dependent. And then we are having a third stochastic processes where the process itself is is spatial dependent, but occurrence of an event may depend upon certain other factors. So such kind of processes is going to generate a set of event or incidents. So what we do is in case of clustering, we like to know that or we try to identify how those different patterns are there. So is those are those patterns are basically some kind of having an spatial dependencies, or there are no spatial dependencies in those cases. So let's have an example of these four different four different spatial patterns. So these patterns has been outcome of any spatial processes. In the first case, we are having a few data points which looks like quite distributed in this whole regions, where in the pattern 2 is basically we are having a set of data points which are clubbed together, and in between we are having a large amount of gaps. The third pattern is a kind of where we see that which is just a combinations of these two. So it means like we're having a slight amount of clustering, but as well as we're also having a the occurrence of event in term of where we are having a randomness as well. So it's a combinations of both. So it is having a few patterns in term of clustering, and as well as this is the few points are which completely looks like a random points, where in case of fourth point the processor itself looks like that there's a completely a regular pattern. So it means like at every fixed occurrence, every fixed distances the event has occurred. So any spatial process is generally going to generate an event which will display a similar kind of pattern whatever we are seeing over here. So in this case, if we would like to know that is these patterns is having some kind of spatial dependency or not, then we have to carry out the cluster analysis, especially in the cases like pattern 1 and pattern 2. So by visually looking at these two patterns, it may look like that there is some people may say that there is some amount of clustering. Some people may argue that there is no clustering attached to it. So it means like we need to have some kind of a measure which will tell that any spatial patterns whatever we observe is actually having some kind of a spatial dependency or clustering or independence or not. So those kind of measures has to be defined. So under the basically these processes, what we try to do, we try to identify those measures, and then we finally conclude that is the process, underlying process is a regular one or a cluster one or a random one, or and how much is cluster, regular, and so on. So that measures can be derived. And there are also a few other things which we need to sometime need to carry out, that the different event whatever has occurred, is those the event are actually the measure of those events are having some kind of spatial dependencies or not. So means that if an event has occurred here, whatever values which we'll see in this case is the value in the nearby is having some effect due to this co-locations. So such kind of things we need to model it, especially in the spatial clustering. Generally, the attribute based clustering, which we call, in those cases what happens is that you simply take the attribute values, you ignore the spatial location of those events, and then based on that you simply do a clustering. In those cases what may happen is that there may be a lot of artifacts, because in any kind of clustering algorithms or any kind of the modeling, or let's say in the regression models and so, we put an assumptions that the each of those events measurements are actually completely independent, and the measurements are random and independent. But due to the special processes which are which basically links them, so that incident or that assumptions basically violates, and due to that there will be a kind of lot of artifacts will get generated, and as a result there may be a lot of interpretation of different measurements. So we have to consider those factors while doing a spatial modeling. So let's see what are the different spatial relationship which exist in spatial processes. So generally, if we find out, the most of these spatial processes will have some kind of autocorrelation. So it means that there will be a few values, and the values near will have some kind of similarity between them. So that's basically if you know any one of these values, yes, with the auto correlation properties, we can somehow predict that what may be the nearby another point values. So that's basically due to the processes, spatial processes generally will occur in a specific locations, and their values are actually will be co-located. So it means like each of those points are outcome of a same processes. So that's why there will be a kind of measurement which will get impacted by this. Apart from that, there may be also a kind of influence of distances. So let's say for example, if I would like to find out a temperature at these locations, and temperature in any city at one location and maybe of 10 or 20 kilometers from the weather stations, the temperature is not going to change much. But if you would like to talk about the pollutions and so those, in those cases what may happen is that at a point there will be a few values, but at another point, maybe at 50-meter or 100-meter away from the road, the pollutant content in air may be a lesser. So that's so those, so it means like in few there are few factors which are quite heavily dependent upon the distances, where there are few variables like temperature which are not so much dependent on a small distance variations. So generally we need to model, so generally these processes we need to model that what is the impact of distances. That's what we look for it. In case of aerial data sets, we look for a kind of connectivity. So it means like what is the effect from on this polygons by neighboring polygons is generally is being modeled on the basis of their connectivity. So if they are having some kind of connectivity between these two polygons, then there are chances that these values will have some kind of weighted influence on the values in at the center of these polygons. So these relationship or the connectivity is being represented as a kind of connectivity graph, or this is also called a weighted connectivity matrix. And in this case, simply the matrix is basically giving that what is the values or which all those polygons are connected. So these two are basically a cases where values at one locations are and the measure at the another location are being weighted with respect to the distances or with respect to the connectivity. There are also some kind of spatial relationship which we look for is a kind of regularities or irregularities. So in those cases, let's say these two patterns are there where these two patterns are quite regular, where in these cases we see that there may be a few points or places where the occurrence has occurred, values are there, where in some cases the values are not correlated, where in the cases at the bottom we see that each of those values, the nearby values, are actually completely opposite to that. So it means like there's a negative correlations at the bottom, there's a positive correlation between two values in these cases, and the values bit at the between is actually in between these two. So the whole the processes generally we try to find out the measures where what are the ways to find out these relationship. That's what we'll be seeing into in coming slides. There's also an impact of spatial relationship, and which is called a covariate. So it means like the spatial patterns, it may be dependent, not only dependent upon the spaces, but it may also dependent upon some other variables. So this is like a kind of temperature distributions and the corresponding point distribution which has event has occurred. So based on that, what we see is that in these cases the areas where the low tone yellow values are there, or in around 150, and so we are seeing that there's no event has occurred, where in the cases where we are seeing a kind of high values, there's a high amount of clustering chances, and also at the other opposite side there's a few chances that at the lower side you're having a lower value. So it means like there is some kind of relationship between the event occurrence at these locations and with the corresponding temperature values. So these kind of spatial interactions where the space and along with the other variable, both of them actually influences that what may be the patterns which get generated, and that is being shown in this case. The other example is in which is shown, and this is a correlate data sets. It's a quite famous data set, especially available in these cases. So in this case, what happens, what has been done is that the data set is in this case is actually having an larynx cancers, and then we are also and there's a mapping of larynx and lung cancer. So generally the lungs cancer has been done, and out of those lung cancers few larynx cancer has been mapped, and there is also a kind of a source incinerator, or this is the older source incinerator. That location has been shown over here. So in these studies what people try to find out is that is there any kind of relationship which exists, or the lungs or the larynx cancer is more wherever the incinerator is there or not. So these kind of statistical strategies can be done, and this correlate data is again freely available data sets. This at the bottom also we see there are two different data sets which looks like that the set of event which has occurred at one locations, and this is the another event which has occurred. So this basically is showing the two data set. One is rented house, and another one is the which was taken in by someone's. Another one is the owner of those houses, and all those places where vacancy is there. So it means like the people who own it, they have also vacated their house, which is being shown in blue color, and the people who were on the rent have also vacated those places. So this shows that there is a kind of similar pattern in if you are owner or if you are not a owner of a particular houses, but still in these areas the houses are uh, empty. So this gives the kind of indications that there is a ownership is not a factors for the scenarios, but rather than some other apart from the ownership also there might be some global factor which may be affecting these tools. So whenever we want to find out or try to understand that is the any specific spatial pattern is actually a combinations of or is being influenced by some other factor, then in those cases we do a spatial pattern interaction studies, and in that cases what we do is we carry out the event occurrence where we take care of or we give a weightage to the other factor as well. So generally that is being represented as an Poisson's processes. So it's basically an event which may occur randomly spatially in this place, plus there is some weightage of the covariate values, and that's how the density function is being used to take care of the spatial point patterns interaction where the covariate plays an important role. So let's say that after seeing that few of the cases where what exactly is the spatial clusters, basically how what are the different processes and how those processes actually influences that processes may be due to underlying processes, or there may be a covariate which may had caused some kind of spatial processes, and those processes results in a few events. So based on after getting those events, we would like to find out is those what is the nature of the underlying processes based on the patterns. So one of the basic tools which is available to us is actually a clustering tools, and under this clustering tool what we do is we simply take weighted values. So weighted values we take it either attribute weight values, or we give an equal weightage to the attribute, or just location is being considered. So if you just ignore the attribute values and take a locations into the considerations, then in that is called basically a centroid or mean centroid based values. So under that what may happen, what is being computed is that we see that there are a lot of points are there, and we can say that all these points are concentrated at these locations, and due to that there is a kind of variations in one directions. So these variations generally says that the distribution of all these points are in a specific direction, or this is not this is also called an isotropic or non-isotropic processes. So it means like at any places if event is occurring in a specific direction, there is a causes of an event which has occurred and that is getting influenced. So direction is playing an important role. So those kind of things, if you want to identify that is their direction, the points are having some kind of direction or not, then in those cases the mean center and standard deviations can be computed. Then we are also having a spatial clustering based approach where under the point based the mean center clustering is being shown. Then we are also having a distance based clustering cases. We'll see a few example of that. And all these spatial clustering are actually dependent upon a scale. So the scale generally means that are you going to consider the influence of an incident on this point to at a certain distances, or you will consider that those influences are actually distance dependent or it is independent. So it means like if an event has occurred, let's say in a Dehradun, so we say that occurrence of that event is influenced by Delhi or by Mumbai. So in one cases we can say that any incident or at one locations in Dehradun is having an equal weightage to event occurring at Delhi and Mumbai. So even though the distances between these two metros are quite large, but we are giving an equal distance effect. So that is called a single scale dependence. So it means like as you increase the distances, there will be a few influences. But in some cases, we may be having a multiple scale effect. So it means a one scale will see one particular regular patterns, another scale, as the scale changes, the patterns completely may look different. So these things which will have a look of that. So simplest example of a centroid based analysis is that these are basically a temporal event. So it means like it is showing uh, a few places is being shown in the in on the points, and then what we are having is we are having three separate time period. So in one time period, what we are having is we are having a centroid located at red dots. Then in another cases, it has moved in one directions, and then again in the third time period, it has come back. So what it indicates is that there was an influence of a slight pull of the event in a particular direction for short period of time, and then again it has come back. Now, these basically helps in finding out that is there spatial processes which are, if it is linked which is linked to surrounding locations, and if there is a changes into that locations, and if that mitigation plan has not been carried out, then event may occur at the naturally where it was occurring. So these kind of centroid based analysis can be carried out to find out that the post and pre activities, that has there been any influence of on policies or not, that we can easily identify. So let's come to now the formally the definition of spatial clustering. So generally, whenever we say spatial clustering, so then it means like our job is to find out a group of occurrence of events, and these group has to be of sufficient size. So it means like there has to be enough number of members in that group, and we also like to know that is that clustering or grouping whatever has happened, has it been happened due to some chances, or it is actually some underlying processes which has resulted. So chances means that there is no specific event, but still somehow at one instances that that particular cluster has occurred. But probably if we repeat the same processes, then those clusters may not occur. So that's so we do try to do a comparison of that. So whenever we do a spatial clustering, our job is to find out a group, and then we have to find out that group for a specific measures. In term of the outcome of that group is that we need to have some sufficient number of points or events within that group, and we do a small testing that is this group is actually an occurring by chance, or it's like some kind of spatial processes which has occurred. So spatial clustering is supposed to provide these three informations. So like if whenever we say group, so it's basically a location of occurrence of the event. So it means like single patient disease occurrence, as we have seen in the John data sets, and the aerial data set, basically the recent COVID data sets, whatever we see. So those are the two different data sets, and we would like to know that grouping of those points based on the spatial or an aerial, that is the sufficient number of groups are there, or sufficient number of members are in these groups are there, and has those groups are actually occurred randomly or not. So that's the basically the job of any spatial clusterings. And generally these spatial clustering uses is basically to demographic studies, especially like we do a grid based sampling at one locations, and then we try to do an aggregated district level or a kind of any kind of administrative boundaries levels. The aggregations has to be done of those measurements, so that's there it's being widely used. We are having in some kind of hotspot identifications. We also try to identify the co-occurrence of the event to source, as we have seen that the influence of covariate and so on. So to carry out that spatial clustering, there are a lot of different technical methods like cluster and outlier analysis, hotspot analysis, spatial autocorrelations, and generally we also look for a causal analysis. This is basically a covariate based analysis techniques which is being used. So let's take a simple objective that how do we measure a specific clusters. So generally, if we want to measure an spatial processes, so this is being measured in two different ways. One is that we simply say that an event has occurred in a specific locations, and is this location is actually some kind of the incident has occurrence of that event is evenly even, or there is some kind of clustering is there or not. So it means like we just try to find out the intensities. So basic assumptions in such cases is that at any processes, so this is just an outcome of spatial processes. So whatever the measurement which we are seeing on these cases, in these cases basically it is assumed that this event would have occurred irrespective of the location. So let's say first event has occurred at this location, and if we would repeat this particular incident or even these processes again, then probably the occurrence of this point at another location is equally likely. So it means like which has started randomly here may start it randomly here, and so on. So in such cases, we say that the points, whatever we see in the locations, are having some kind of uniform density or distributions, or there is a non-uniform density and distribution. So this is first way of identifying and carrying out the analysis. So in this basically helps us to identify that is there any cluster chances of a cluster occurrence is there or not. That's basically the job of identification is being done. So in this case, what we do is we take consider to be that at any places the event, whatever the number of event which is going to occur in specific locations, that is fixed. So generally, to find out that, we simply take the number of event counts and take an area division of that. So that's basically gives the density of events per unit area. So if we have that density per unit area, and based on that we simply say that this occurrence will be there. The another way of looking into the measures or the measure which we try to identify for a cluster is basically trying to find out that is the each of the values at a particular locations are having some kind of dependencies or not. So it means like wherever the incident has happened, the another instance of that event is equally likely, or it is likely to occur in a same locality, or it is also likely to occur an equally distance from that. So these are the basically another way of looking for spatial clustering. So generally, intensity based is basically we try to find out the number of point which has occurred in is equal or not. And another case is this, we try to find out is there any specific type of cluster is there, or uniform is there, or there is no uniformity in a cluster. So this, whenever we look for a processes like this, so it means like the event occurrence is not dependent upon the space, but rather than it can occur at any places. So that's what we call it as a CSR, or complete spatial random processes. So what it means is that any event whatever which has occurred, or the data set which represents that the event has occurred, and if the next time if you take the measurement for those events, then the intensity of or the variation or density of those values is not going to change. So the event may occur at different places, but in a specific on an average any number of event will remain constant. So that's basically the crux of the spatial references, especially the complete spatial randomness. And in this cases basically whenever we do any kind of spatial clustering testing, so we try to always measure with respect to CSR properties. So CSR properties basically tries to find out the densities, and in this cases the null hypothesis is that basically the processes may occur equally likely in all the places. And then what we do is we simply do the spatial clusters and the events or the values which has number of event whichever has occurred at specific locations, and what is the observed values. So if those two are actually matching or not, and based on that deviations we compute the deviation square values. That is nothing but a chi-square test is being done, and that basically tells that is the process is random or not. So if you're having a large deviation, so it means like there is no matching between CSR and the events, and the processes in those cases will say is not random. So not random means that the process may be completely regular or it may be completely cluster, but it may not be a completely random. So seeing back into this example, so if we say that we are having a very high value of chi-square cases or the deviations, so either this may be due to this or due to this, but it may not be due to independent event or random event. So that's basically to strike it out, the CSR test is being carried out, and that's what we do it in those cases. So to carry out the CSR test, this is basically also called an quadrature based analysis, or this is also called a global density analysis. So in this case what we do is we take a regular interval of grid points, like in this case we are having a 4 by 4 grid points, and based on these grid points what we do, we count the number of event which has occurred between this, and then we compare it with what will be the average. So let's say if you're having 64 points available in this whole area, and then if we say that there are 16 different compartments are there, so then in those cases what we look for is that we try to find out that the total number of event per boxes is supposed to be 4 if it is completely random. So in those cases the total number of points in each of those boxes are supposed to be 4, and if there is any deviations from that, then we can say the processes is not random, and so that can be computed in that way. So the example, whatever the 4 different patterns which we have seen, it's basically showing the number of counts and it has been divided into 4 different sections. So as we see that the number of points in the completely regular patterns in all the cases are constant, so it means like there's equal number of points which is occurring. In case of randoms, there is a variation. So at one pocket we are having a large amount of point, another pocket we are having a more or less similar amount of points, and then we are also having a kind of completely non-random cases or completely random cases where the event of occurrence of is almost or try to be an average nearby, and that's what we are seeing it in this case, where in case of clusters what we are seeing is that there are a large number of points which is occurring in few of the quadrature, but in other quadratures this is basically a smaller one. So this basically gives, and based on that we can say that this is a highly this process is almost non-random. This process is completely random, where these two processes are non-random along with the regular pattern which we are seeing in these cases. So if you the density based maps, generally what happens is what we do is in these cases are that it is basically dependent upon the number of the boxes or the spatial scale which we take into the considerations. So like if we are having these for 2 by 2 boxes, which is the whole area is being divided into 2 by 2 grid, and if we start increasing these grids, then whatever values which we got, where it may say that at initial cases it will say that there is not random, but what we'll realize slowly is that it will be a kind of showing that there is some kind of clustering or non-randomness has occurred. So these kind of limitations are there, which is actually which shows that for the carrying out the cluster analysis you need to have a kind of scale dependent, and before taking any kind of measurement we need to know what should be the optimal scale which has to be carried out by the analyst. The other problem is that it doesn't bother about the grouping or the interdistances between the event points. So like these two patterns, whatever we see based on the quadrature analysis, what we'll find out that there's an equal number of event which has occurred, and in those cases it will easily indicate that there is a both two patterns are actually a kind of regular patterns. So I mean, like, there's not randomness will not be shown in these cases. So to differentiate these two is not differentiation of these two is not possible in case of density based processes. So to take care of that, what we is being done is basically the distances or interdistances between the event is also being taken into the consideration. So it means like we take an one point and we take the another point at some distance, and that distance is being weighted. So whatever values which we consider to be here, what we'll do is we'll take a value of this point and divide it by the inverse of that distance, and that's where we'll calculate the average distribution of that part, the points and or the densities, and that will give a kind of values which will look like this. So in the earlier cases we are able to not differentiate these two cases, but after doing a simple kernel based envelope, which is basically a distance based functions, we can easily differentiate these two patterns as we can see it over here. But the problem of again the kernel density functions is that this visually gives the kind of cases that we are able to differentiate these two cases. But if you want to compare that this is a higher band cluster or it is having a large clustering pattern compared to this, the distinction of that is not completely uh, possible, and that's the basically a demerit of kernel density functions. So to carry out so we see that in the previous cases generally what we see is that the distance is going to play an important role. So kernel density function is not helping for that. So for that what has been done is basically a specific functions has been created. So that is basically this is also called a single scale G function. So it means like it takes at one it takes an event, it computes the neighboring distance, and then nearest neighbors it counts, and whichever the nearest distance, that nearest neighbors distance, that is getting computed and is being kept in as one of the attribute for each of those points. So if you are having an n number of event which has occurred in specific locations, so each n number of event is going to have n minus 1 neighbors, and so what we do is in these cases is that we compute the distances for the nearest neighbor. So it means the neighbor which is nearest to an event is getting computed. So that's what is being represented in this formula. So it's basically gives the nearest neighbor's distance value is being computed, and based on that it gets compared with respect to your density functions and or with respect to with respect to your the random processes or random Poisson's processes. So if your point, if your distances between the is and these distances are again, so these basically distance is as you can see is that at a distance these basically distance has been into 4 different classes. So 4 different classes is there. So at 1 unit, maybe 1.25 unit of distances, we are having around 20 different neighbors. So between 0.25 to 0.5 we are having again around 12 or 13 different neighbors and so on. So that's the basically a distribution of all those points based on the nearest point what we see. So based on these binning processes, as we can see that these two histograms clearly differentiate that where exactly the clustering is occurring and where the clustering is not occurring. So in case of clustering, what we see is that the nearest distance to neighbor is quite high at the beginning, but slowly it start decreasing. So it's a kind of a drop. So initially there will be a large values of nearest neighbors. So it means like the nearest neighbors are quite close. Then slowly there will be slight distances, and later on all the to find out a neighbors which is quite far will be a very less. So that's what the distribution which we get. So this kind of pattern, if you see, so this basically shows a kind of distributions, or a kind of distance based distributions for a cluster based patterns, where in case of regular patterns there will be no neighbors at a specific distances. So at the beginning there will be no neighbor, then suddenly at a particular distance you'll find out all the neighbors are within the range, and then after that there will be a no new neighbors, or nearest neighbor is not possible. So this is the second cases where completely regular distribution is there. So what has been done is, there's a metric G is being defined. So in this case basically a cumulative graph is being plotted in these cases, and one is based on the Poisson's processes, and another one is the actual observed values. So if your distances are matching between these two, then it means that your processes are quite random and there's no clustering or regularity is present in your cases. But if you see a kind of differences like these two gaps, so the first cases, if at the beginning there will be a sudden high values, after that there will be a sudden rise, and then again at a very small distances will be exhausting with all the nearest distances, and then it will remain constant. So this is the cases whenever we see. So this represents a kind of clustering scenarios, where in case of regular cases it will be a downward trend. So it means for a very large amount of time there will be no neighbor value cannot be found for a particular distance, very large amount of distance. Suddenly there will be increase, and then again it will remain constant. So this basically shows the completely regular pattern. So this is basically called a G function based methods. And this basically the G function methods just measures the event and the nearest event which has occurred. Complementary to that is actually an F function. So F function basically tries to find out what is the empty space in between. So in this case what is being done is that you take randomly any event. So you need not have to take an individual point, rather than, let's say I take this point over here and I try to find out what is the nearest event point which has occurred from this place. So that's how it gets computed for each of those locations. So generally this is being done with very fine scale. So let's say this whole area will be divided into 10 by 10 segment, and each of those segment we just look for a nearest neighbor centroid of that point, and that's how we get a two-dimensional distribution of points. So in this case, whenever we say an F space, so if you are having a clustered point, or if you are having an random locations, so in the random locations what we'll observe is that the empty spaces are almost distributed across in the whole areas, where in case of cluster cases the nearest neighbors or the empty spaces will be again clustered. So these two can be observed in terms of distances, and from the graph we can easily compute that. So if you're having a completely random processes, then it means that your empty spaces will again match with this spatial distributions. So if you see, this is very similar to what we see in G poise or the G functions. Only difference is that instead of an event distance, now it can be any event. So this will match exactly in the cases. So it means like empty spaces are almost randomly distributed across, where in case of clusters what we will observe is that the observed value will be lesser. So it means like there will be a very small amount of empty spaces which will be exhausted at the beginning, but slowly that empty space will be quite large. So whatever values which we'll see, that empty space will get increases, and this is basically an F based functions which is being done. Then there's something called K functions. So this is the K functions basically takes care of distances not at a particular distances but less than average density. So it means like it takes a distance, counts the number of points from this. So within that there are few number of circles, then the circle radius gets increased by few amount, again the new count is being done, and so on till a particular number of circle is being counted. So within this scale, the number of events are getting computed, and then we take an average of that values. So this basically helps us to identify multi-scale regularity and irregularity what may occur. So like in these cases, at the beginning there are a few clusters which are occurred, but these clusters are again seems quite regular. So at another scale, the patterns are becoming irregular. So at smaller larger scale, or distances between these points is lesser, so we see a kind of random patterns, but slowly again it gets converted into a regular pattern for larger scale. So such events can be identified in using a k-scale matrix. Then we are having an aerial based techniques. I think this has been already might have been covered, but in these cases basically what we see is that distances or connectivity between the neighbors is being taken. So this is basically a weighted distance is being taken. Now this weight can be based on the attribute, or it can be an connectivity attribute. So what we do is, generally at the beginning we have seen that in case of aerial analysis, we try to find out the neighbors, and neighbors weight or neighbor values can be considered to find out a weighted correlation values. So these weighted correlation values is being computed, and that's what we call it Moran index values. So in these cases, generally what we do is that we take a values at one for a one particular polygon and its nearest neighbor values, and based on that we get a kind of correlations graph, where we say the value at this of these polygons and the value of these polygons on the y-axis, or all the neighbor axis is being taken into representations. So if you're having a high amount of clusters, then in those cases the correlations will be quite high. If there will be higher values cluster, lower values clusters will be on the bottom side, and then there will be an in between which will be given at low values and high values. So that's what we are seeing over here. So we are seeing a high values cluster in these cases, and this is low cluster in these cases. So it means the lower values clusters are there. So this is basically an hot places where the event is having some values correlated, where these are the places where event is not having any kind of there is a relationship but values are not high. So and in between there is no significance differences is being found out. So to do an interpretation of simple that, if you are seeing an Moran index value 0, then it means that your pattern is completely random, there is no relationship between these two polygons. And if your values are increasing towards, then in those cases you will be having a high amount of clustering, and if it is negative towards, then you're having a low amount of clusterings. So this is just an whenever we do an interpretation of any Moran indexes, so we take a kind of significant p-values and z-score. So this is just an example where it clearly indicates that these are the places where we are having a kind of clustering of those zones, and this clustering basically indicates that not only there's a hotspot, but around that there's a kind of spatial relationship which is existing. Apart from that, there is another methods called Getis-C ratio methods. It's very similar to Moran indexes, but it is slightly scaled into 0 to 2 values. And in these cases, what happens is that instead of taking differences of the from the mean of individual values, what we do is we simply take the covariate values. So two different polygons neighboring polygon values directly is being taken. There's no this is not being taken as a covariance what we have seen in the index in case of Moran indices. So this is basically gives, and the interpretation of this is basically is that if you're having an 1, then it means like the Getis value 1 means there's no correlations. If you're having 0, then it means the positive correlation relationship, and if it is nearer to 2, that means there is a negative correlations. These are also called an LISA. So this is basically a global value. So it means if there are n number of districts in these cases, like 700 plus districts, so all the 700 plus districts will be used for computing either C Getis-C values, or it will be for the Moran indexes. But there are slight modified values which is called a Lisa. Lisa basically looks for a local clustering. So in those cases, what we do, we limit the amount of neighbors which we are going to consider, or the weightage whatever we'll take, that will be specifically limited to a specific locations. So this basically gives the localized spatial autocorrelation. So within the global autocorrelations, then again, if you want to find out localized correlations, then that can be done with the help of Lisa. Then there's another metric called Getis-Ord Gi. So it's basically helps us to, or it's basically a kind of weighted attribute values is being taken. So you're having, like in this case, we are having a values of number of active COVID cases. So based on that, if we combine based on these Getis values, what we do is we get a certain amount of Z score. So that Z score basically tells that is the variation is independent, so it means that there's no correlations, or there's a correlations is existing between 2 points. So based on that, this weighted measurement is being taken, and we get a certain amount of Z score for those values. So all those Z score values, wherever we have higher and lower values, then in those cases there is chances of clustering. So that's I'm like, wherever we are having a values which is higher. So like in these cases, all the values which is not which is beyond the 2.5 standard deviations are being actually is being shown in these cases. So these are basically an high Z score values, and we are also seeing that the p values are actually quite significant in those cases. So we can say that these are the actually, we can definitely say that these are basically a set of cluster points of different events. So these are the few techniques which is available to us, and that can be used for finding out a few aerial or the point pattern based clustering, especially the spatial clustering. We haven't discussed about the temporal factor also, which can be taken into that, and as well as simulation. So generally simulations, what we do is we take a few measurement like this, and then again we try to resimulate with the same Z score values, that is it really quite significant, or if the values, whatever the Z score values which we get, is actually the another possibilities of getting the same Z values, and are how likely is that this cluster is going to occur or not. So that particular portion we haven't discussed today, but those are the basically the extension of these clustering techniques whatever we have.